going to have the location of the vertical asymptotes if they exist, and then state the domain of this function. How do we find vertical asymptotes? Anybody remember this from earlier? What creates a vertical asymptote?
When something is divided by 0.
Good. So when we're dividing by 0. So if we're looking at number 7 from your guys' homework tonight, what is going to be our vertical asymptote in this case? 3. What 3? X equals 3. Oh, let's go back to 3. Okay. So just so we start to have a little bit, I guess, more proper communication. This is the vertical line x equals 3, because x equaling a number gives us an actual vertical line. So x equals 3 is what we're looking for. And so what we would anticipate when we eventually get to the step of graphing these is at x equals 3, there's going to be this line we can approach but never actually touch. And then we're going to have these other asymptotes. What happens if I find the zeros at the top of the numerator up here? What is that going to give me?
The y asymptote.
Not quite. Close, like kind of the right idea, but
Y-intercept?
close still. How do we find, first of all, what happens if I make this top 0? Does the whole thing become 0? Is there still stuff going on?
It's 1, because like if you divide 0 by 8, it's
If I
1.
divide 0 by anything, what happens? It's 0. So what am I finding? We're finding the, what have we done the last 2 weeks? The zeros of the function, which are also the x-intercepts. Good. So if we find the zeros of the function, what we did is you plugged in 0. And so anything times 0, this x minus 3 will just disappear. So all you need to do is actually find the 0 at the top. So our x-intercepts at x equals -2. And so, and we'll talk more about this, how to graph these, but we'll see that we actually end up with graphs that'll kind of look like this. And then later on today, we'll talk about how multiplicity of your asymptotes is going to tell you if you have a sign change here, or if they stay at the exact same point where there's no sign change. And so it'll behave similar to what we've seen in the past. But oh, and then the domain of this function. So what would my domain be? What's the only number I can't be? It can't be 3. So there's going to be a couple ways I'll let you guys describe this. X is an element of all real numbers where x is not equal to 3. Okay, so you'll see that in other math books throughout. So you could write it that way. Otherwise, the interval notation that we're used to doing is from -infinity to 3 unioned with 3 to infinity. So we could view it in interval notation as well. Those would be the 2 acceptable formats. Okay? The next thing we're going to take a look at is identifying vertical asymptotes again. And then we're going to state whether the value is going to have a sign change or not. So in this case, number 15 from your homework tonight, x plus 1, if I found a 0 up there, what is that going to give me? X would equal -1, but what does that represent? The x-intercept, good. So I know this has an x-intercept at -1. Okay, and we found that because we plugged in 0 for y, basically. Okay. And then that makes the whole bottom just kind of disappear. We can factor out the bottom into an x minus 3 and an x plus 2. So where are my 2, in this case, vertical asymptotes? One of them is located at x equals 3, and the second one is at x equals -2. Okay? In this case, what you're going to do is we're going to look at the multiplicity just like we did with the x-intercepts. We're like, oh yeah, odd multiplicity went through. So realistically, if we think about the y values as it goes through there, it goes from positive to negative, or if it was coming from the other way, negative to positive. So there's a sign change for those odd multiplicities. And then just like we saw with even multiplicities, it bounced. So it either stayed positive or it stayed negative. Same idea will occur here. There's a multiplicity of 1 and a multiplicity of 1. So both these will have sign changes. Okay? So this will change. And right now we won't worry too much about whether it goes from positive to negative or negative to positive. We'll just know that there is a sign change. And for both of these. Okay, so that'll change. This will change as well. And then you guys won't need to do this quite yet. But we'll kind of guess what this starts to look like. So at x equals 3, we're going to have a vertical asymptote. At x equals -2, we're going to have an asymptote. We're going to see that there's a horizontal asymptote at 0, and we'll talk about that on the next problem, how I knew that that existed. And I'll know that I crossed that asymptote, because you can cross horizontal and slant asymptotes, but not vertical ones. Okay? This will cross right here at -1, which happens to be our x-intercept. And then the y-intercept is at -1/6. So I've got a couple key pieces here. I know that this is going to start that way, and we'll talk about that more in the days to come. This will have a sign change. So it goes from negative to positive, and then it works its way down through here. And then again at 3 has a sign change, so it'll be up top here. So we'll talk a little bit more about how we're going to be able to actually identify what that graph is, but for today, all you need to worry about is the dark blue stuff. And where are my vertical asymptotes? And does it have a sign change? Okay? So that's what we're looking at for the second part of tonight's assignment. And then the last part is going to start to look at horizontal asymptotes. So we'll have a quick discussion about how we can identify where those are at. So given something that looks like number 21 from your homework. In this case, we're going to determine if a horizontal asymptote exists and determine if the graph will cross that asymptote. If so, where does it cross? So for horizontal asymptotes, what we start to look at is there something we approach as we head off into the infinities, whether it's the negative infinities or the positive infinities? What are we approaching? I think in the book they're going to give you kind of this general guidance where you'll see if the top degree is equal to the bottom degree, you'll approach, so your horizontal asymptote will equal the, trying to describe this in less crazy wild vocabulary, the top lead coefficient, so let's call it top coefficient, divided by the bottom coefficient. So what we mean by that is, let's say we had an example of something like 3x squared plus 2 over 4x squared minus x plus 1. Okay, so let's say this was one of our examples. My highest degree is squared, both on top and bottom. So if the top degree equals the bottom degree, then our horizontal asymptote is going to approach this coefficient 3 over 4. So my horizontal asymptote is at y equals 3/4. Okay, the reason that happens is as x gets really, really, really big, that 2 doesn't really matter. As x gets really, really, really big, the negative x plus 1 doesn't really matter. So what you're left with is 3x squared over 4x squared. So your x squareds are going to cancel because they're the exact same value. So you really are just approaching this 3 over 4 as you head off into foreverness, like the really, really big numbers. Okay? So a horizontal asymptote, when your degrees are the same on top and bottom, will approach whatever your lead coefficients are. Okay. So what I mean by that is as I head way off into like that direction, it doesn't matter what the smaller degrees are, because let's say x is a million. So x is a million, so 1 million squared is a huge number. 2 does not even matter compared to, what would that be? That would be billions, trillions. So 1 trillion, not even close to 2. Okay? Same thing here. A million squared is way bigger than a million. And so this starts to not even matter. So what you end up with is 3 times a million squared over 4 times a million squared. So the million squareds will disappear, so you're left with just 3 over 4.
No, I get that, but we got 3x squared plus 2 and 4x
I totally just made that up. This is just a made up example. Because the ones up here are going to be a different example. So we'll use this one next. So if the degrees are the same on top and bottom, which is this made up example, this is made up. Made up. Okay. Then it'll approach the 3 over 4. Okay, that makes more sense then?
Yeah.
Okay, cool. The next piece you'd then be looking at is what if, for example, from your homework tonight, we'll take a look at this one. What happens if the degree on top, so the top degree, is actually less than the degree on bottom? So in this case, similar approach. Let's think about as we get really, really, really big. So let's use that example of a million again. 2 times 1 million minus 3 is roughly 2 million. 1 million squared is a huge number. Plus 1 is still that huge number. What are we approaching? A million over a really, really big number, 1 million squared. Or think about it on a smaller scale. Let's just think about 10. 10 on top, so 20 over 100. What are we approaching? And then we go to 1,000 over 1,000 squared, which is a million. What are we getting closer and closer towards? 0. Because this number on the bottom is getting bigger way faster than the top is because of that squared factor. So we're going to approach 1 over infinity, which is 0. Okay? So when this happens, our horizontal asymptote is y equals 0. So anytime you have a degree on the bottom that's bigger than the top, we'll approach 0. So for your homework, the horizontal asymptote is y equals 0 for number 21 because the degree is bigger on bottom. Yes, Casey?
Let's say that on the bottom it was just like 5x plus 1. Is it still the same?
So if it was 5x plus 1 and then 2x minus 3, the degree are both 1 on top and bottom, so we'd approach 2/5. Yeah. So then determine if the graph will cross this asymptote. How you determine that is, here's my asymptote. I'm going to see, is there actually a value for this? So we're going to take 0, plug it back into the equation. And so we'll see 0 equals the 2x minus 3 over x squared plus 1. If I multiply both sides by this x squared plus 1, it will equal 0 still, because 0 times anything is 0. And so then we can just add 3 to both sides. And then we'll see that 3 halves equals x. So yes, we will cross this asymptote at 3 halves. And so if we look at this as a graph, we noticed we solved and said that our horizontal asymptote was here at 0. We're going to cross that asymptote, however, at 3 halves. And then we can also find the, in this case, does this have a vertical asymptote? We try to find that as a 0. What do we end up with? X squared plus 1 set equal to 0. What do you end up with? You'll subtract 1, take the square root. What's the square root of -1? I. So do we have real vertical asymptotes? No, they'll be complex, so they won't actually appear. So this is one of those weird graphs. It'll actually look something like this. it'll come through here and give you a little bit of a bend, and then it'll flatten back out. So we'll end up with -3/1. That ends up being our y-intercept. But that's kind of what that graph will look like. It will be weird. So if you guys want more of a visual representation, definitely type it in the calculator today and just kind of look at what's going on. We'll talk about some more tricks on how to actually graph these over the next couple weeks. But I wanted you guys to see the last piece that will be on your test before you take off the break. Okay? So this will be the entire test. We're going to have the factoring, find the polynomials. You're going to be able to use the remainder theorem using synthetic division. We'll have graphing polynomials, and then the last piece is graphing these rational functions with vertical and horizontal asymptotes. All right.